The en route phase of flight starts at 1500 feet above the departure aerodrome and ends once the aeroplane has reached 1500 feet above the intended destination aerodrome. Similarly with other phases of flight for Class A aeroplanes, the en route regulations account for engine failure. Therefore, manufacturers and operators of Class A aeroplanes must ensure that the performance of the aeroplane subsequent to engine failure is still able to meet the regulations. Generally, once the en route phase of flight commences, the pilot workload is reduced. The autopilot and autothrust systems are usually engaged, and this relieves the pilots from basic flight maneuvering, allowing them to concentrate on other things. Therefore, during the en route phase, most pilots carry out in-flight monitoring, flight performance data checks, and review emergency procedures. Despite the relatively light workload for the pilots during the en route flight phase, there is a lot of information that you need to understand about this phase of flight. Firstly, we will focus on the climb to the en route altitude. Then we will deal with the en route altitudes and how they are calculated, as well as discussing various flight speeds. Lastly, we will detail the descent, both normal descent and the descent forced early either by engine failure or depressurization. After a normal takeoff, climbing to the en route altitude is a fairly straightforward affair. Once the aeroplane configuration is clean, a set climb profile or climb schedule will be flown. Initially, the aeroplane climbs at a constant indicated airspeed. However, continuously climbing at a constant indicated airspeed causes the Mach number to rise. Beyond a certain altitude, the Mach number gets too high, and serious aerodynamic forces start to affect the aeroplane. In the 737 family, the maximum Mach number, MMO, is 0.82. Therefore, at some lower altitude, the aeroplane needs to change its climb profile to a constant Mach number climb. The altitude at which this change occurs is called the crossover or changeover altitude. In brief summary then, the climb profile involves the aeroplane initially climbing at a constant indicated airspeed, and then, at the crossover altitude, the aeroplane then climbs at a constant Mach number. However, ICAO limits the maximum indicated airspeed to 250 knots when below 10,000 feet. This slightly changes the climb profile. For the majority of the 737 family, the climb profile is 250 knots indicated airspeed up to 10,000 feet. Then the aeroplane is accelerated to 280 knots, and the climb continued at this speed. When the Mach number reaches 0.74, as shown here, the aeroplane maintains a climb speed of 0.74 Mach until the en route cruise altitude. Notice in this case, the crossover altitude is at about 31,000 feet. However, you need to understand what happens to the crossover altitude if a faster indicated airspeed climb is maintained. And for this example, we'll increase the second part of the indicated airspeed climb from 280 knots to 325 knots. Initially, the aeroplane will still climb at 250 knots, but once reaching 10,000 feet, the aeroplane will be accelerated to 325 knots and then climb at 325 knots. Once the Mach number has increased to 0.74, then the aeroplane then climbs at 0.74. Notice now the crossover altitude is lower at 18,000 feet. Therefore, if the indicated airspeed is increased in the climb profile, the crossover point decreases to a lower altitude. Before we proceed to the en route altitude, it is important at this point to briefly detail a few important speeds, most of which you have already covered. These speeds are commonly expressed as Mach numbers. The first of these speeds is the maximum operating speed, either called VMO when using indicated airspeed or MMO when using Mach numbers. For the majority of the 737 family, VMO is 340 knots, and MMO is 0.82. Flying beyond these speeds in a commercial operational context is not permitted and may cause either structural damage or a high-speed stall. The next two speeds are used in reference to describing the range of the aeroplane and were actually mentioned in the en route lesson of the General Performance Principles section. These two speeds are the maximum range cruise speed, MRC, and the long range cruise speed, LRC. When these speeds are referenced in terms of a Mach number, the abbreviation is changed to MMR and MLRC respectively. As you can see from the graph plotting cost and speed, the advantage of flying at maximum range speed is simply because the aeroplane will use the least amount of fuel and therefore have the least amount of fuel cost for any given distance. However, operationally, the faster long-range cruise speed is used. The simple reason why this speed is used is because by getting to the destination more quickly, more revenue-earning flights can be carried out in any given time period. In other words, over a given time period, 4% more flights can be carried out, with only a fuel consumption increase of 1%. However, the long-range cruise speed does suffer from limitations. It doesn't take into account the variable cost of fuel from day to day or month to month, and neither does it account for the operational costs. When fuel prices are high, the extra fuel consumption may dramatically increase the overall cost of the flight, and a more operationally economical speed may need to be flown. The relationship of these costs is explained by the use of a cost index, and the speed flown based upon the cost index is called ECON. This will be discussed next. The fundamental rationale of the cost index concept is to achieve minimum operational trip cost by means of a trade-off between time-related costs and fuel-related costs. The cost index is used to take into account the relationship between fuel and time-related costs. With time-related costs, the faster the aircraft is flown, the more money is saved in time costs. This is because the faster the aircraft is flown, the more miles can be flown for time-related components. It also means that more miles can be flown between inspections when considering maintenance costs. Notice that these costs are minimum at the maximum operating speeds. However, if the aircraft is flown faster, the fuel burn increases, and the total fuel cost for the trip increases. Fuel costs will be at minimum at the maximum range speed, and fuel costs will be maximum at the maximum operating speeds. Adding the time-related costs and fuel-related costs together produces a direct operating cost, or more simplistically, a total operating cost. The flight management system uses the time and fuel-related costs to help select the best speed to fly. You can see from the total cost curve that the speed which gives the minimum total operating cost is the most economical speed to fly. This speed is called ECON. In other words, the minimum cost speed. The value of ECON speed is worked out by the flight management system based upon the value of the cost index. As a formula, this cost index is a ratio of cost of time, CT, divided by the cost of fuel, CF. When fuel costs are high and time costs are low, then the cost index is almost zero. With a cost index of 0, the ECON speed is at the maximum range speed. When time costs are high and fuel costs are low, then the cost index will be very high, and the ECON speed will be closer to the maximum operating speed, so that the massive time costs are reduced. To summarize then, increasing the cost index from 0 to maximum will increase the ECON speed from maximum range speed through to VMO. For most aeroplanes, the cost index varies from 0 to 99 or from 0 to 999. Once the aeroplane has completed the climb profile and has reached the top of climb, the aeroplane will level off at the appropriate altitude. This cruise altitude should ideally coincide with the optimum altitude. You may recall that the optimum altitude was the altitude for maximum specific range, or maximum fuel mileage. As a general rule, this altitude is not constant. As weight decreases during the flight from fuel consumption, the optimum altitude increases, as illustrated in the graph. Therefore, to constantly fly at the optimum altitude, the aeroplane will not actually fly level, but will in fact slowly be climbing in the cruise. On the other hand, ATC require level flight crews to help ensure vertical separation with other aeroplanes. Aircraft must fly by segments of constant altitude, which must be as close as possible to the optimum altitude. These level segments are established within 2,000 feet of the optimum altitude. Remaining within 2,000 feet of the optimum altitude ensures the range is 99% of the maximum specific range. There may be several step climbs during the flight, and the aeroplane may be gaining altitude throughout this process. However, there is a limit to how high the aeroplane is permitted to operate or able to operate. As the aeroplane altitude increases, the thrust that is required to maintain a given speed increases. Eventually, there will be an altitude where the thrust is increased to its maximum cruise value, and it would not be possible to climb any higher without exceeding the thrust limits. This altitude is called the maximum altitude, and is shown on the illustration. However, the hotter the atmosphere, the lower this altitude becomes, and in exceptionally hot atmospheres, the maximum altitude is almost the same as the optimum altitude. Although the aeroplane cannot operate above the maximum altitude, there are other limits also placed upon the aeroplane which could limit its altitude. These will be discussed in Part 2 of the Class A en route and descent lesson.